Whoa, whoa, whoa! We are back talking about atomic absorption spectroscopy and atomic emission spectroscopy. And where we left off were kind of the basics of how the AA instrument works. And we talked about electrons being excited with energy that it's given them, and they start jumping energy levels, and that's the process called absorption. And then these electrons settle back down and they go back down to ground state. And when they do, they emit light, and that's what we call atomic emission. A little statistics, I guess, about the atomic absorption instrument. We now can measure over 70 elements. So 70 elements in total that we can measure, and most of them are metals. Every single one of them really are going to be metals off the periodic chart. That's where AA finds its home, and that's where AA is a little bit different than the rest of the machines that can be found in the laboratory. Concentrations of part per million can be determined, so it can go pretty low. But under the right circumstances, we can also go to the part per billion level. So part per million and part per billion are 3 orders of magnitude apart from each other. That basically means part per million is a speck, and part per billion will be a speck on the speck. That's how small that it can go. So super, super tiny levels under the proper circumstances. Now, most of the time in the field of AA, we are looking at part per million level, not part per billion level. And we have another machine that does part per billion level a little easier now. The instrument is very precise. We've got a 1% relative standard deviation. So that basically means that when I run a sample, and then I run the sample again, and I run the sample again, and I run the sample again, I should be getting about the same number each and every time if the machine is set up and working the proper way. Another good thing about the AA instrument is that it has little interference. That basically means that not too much can be in the sample that will throw my numbers off. We understand going into this that a sample is given to a laboratory, and that sample could have hundreds of different components on the inside. But the AA will allow me to detect only one of those components if I want to, and that is it. And very few things will interfere with that process. So that makes this a very good instrument because I don't worry about contamination in a way of my components in the sample that I'm trying to analyze. I don't need to clean up the sample, in other words. As with any spectrophotometer, we're going to see a relationship between the concentration and the intensity of the light that's getting absorbed. So that basically is a fancy way to say the more absorption I have, the more concentrated the sample is. So if I have a little bit of lead, it will absorb a little bit of light. But if I've got a lot of lead in the sample, it will absorb a lot of light in the sample. And my absorption will go up because of that. And then finally, down here at the very bottom, we're going to say atomic absorption requires that the atoms be in a free state. What that basically means is that it needs to be freed up from any kind of compound. That's the kicker. If we have lead, lead has to be freed in the compound. If lead is attached in any form or fashion to another molecule, and it's not freely floating in solution, but attached to something else, there's a chance that the AA will not see that particular lead because it's not going to absorb the light. In order for this process to work, these have to be freed atoms. Now, what do I mean when I say freed state? Okay, so basically think of it this way. Let's say that I take salt from the pantry. That salt is not in a freed state at all. All right? The sodium and the chlorine are bound up together in a compound. And because of that, this sodium, even though it's a metal, is probably not going to be detected in the AA instrument. I've got to do something else to it first. All right, so let's say most of our samples that get submitted are going to be an aqueous solution. So this NaCl is going to be provided into maybe some liquid, and NaCl's there. Now we know that the NaCl is a salt, and Na will break apart into Na plus and Cl minus. All right, that's something that we know. Okay. However, not all compounds will do this automatically. When we're given something in a laboratory and we want to measure mercury, we have to make sure that mercury is freed up. If we want to measure zinc, we have to make sure that the zinc is freed up. And in this case, sodium chloride breaks apart very easily. Na plus and Cl minus, and these are kind of free. Now, if there's any solid sodium chloride that's still there, and it's NaCl, and it's not broken apart, then this is not free. And because of that, it probably will not be measured. So we have to ensure that these are dissolved and broken and freed up in the solution before we do anything about it at all. Okay? Now, there's tricks that we can use to make sure that this happens. A lot of times in the AA world, we actually see aqueous solutions, and water does a pretty good job dissolving the things that need to be dissolved and broken up. However, it's not uncommon for us to introduce some acids as well. And these acids could maybe be hydrochloric acid, or it could be nitric acid. And this helps those salts or those metal compounds to dissolve up a little bit more. Okay, that's why we use them in our solvent, and that's why they're present. So if you ever read a laboratory protocol that says, well, you've got to make sure that you add phosphoric acid or nitric acid or sulfuric acid or hydrochloric acid to the sample, this is why, because you have to ensure that all of these things get broken apart into the free atoms so that they can be measured. If you just use water for those, well, a lot of it's going to be broken up maybe, but there's going to be a significant portion that will stay together and it will not be broken up. And that's why they're telling you to use acid instead, because they have to ensure that everything is freed. All right, now there's a process that this goes through as far as your sample is concerned, and we call this atomization. All right, Atomization, atomization. And atomization is basically the process of taking a sample and providing it to the AA instrument. However, things have to be done. Number one, it has to be volatilized. That means the solvent has to be gotten rid of. If I've used water, the water has to be gone. If I use acid, the acid has to be gone. I have to go down to the actual components that I want to measure. And number two, we're going to say decomposed to produce an atomic gas. All right, that's the process of atomization. It's the most critical process of the atomic absorption spectrometer that we know of. Everything has to revolve around the process of atomization. So if I want to be reproducible, and I want to make sure that I can reproduce the results from analyst to analyst or from day to day, then this process has to be gone through with a fine-tooth comb. I have to make sure that everything is working properly like it should be. If I want a very precise answer, then the same kind of thing is happening here. I have to make sure that my atomization process is going along as planned because everything relies on the atomization process. Everything. If this is what provides the sample to the machine is only going to find what it sees. And if it never gets to that point, if it never gets to the point of where it should be going through the atomization process, the machine's going to lie to me and it's not going to tell me the truth. And then finally, efficiency is also going to be related to the process of atomization. Okay, so we'll talk a little bit more about the atomization process and about what it does, but that's basically what's going on. You've got a compound that probably has a metal attached to it. That compound has to be broken up, like sodium chloride is dissolved up in a way, and you have to send that through the machine. It gets rid of the solvent, and therefore sodium and chlorine gets presented into the machine and not the liquid solution itself. And that's the process of atomization. All right, so there's going to be a couple of important components for an AA instrument. And we're going to talk about these components in more detail one at a time in the upcoming videos. But these components are going to be the same for any spectrometer that I want to talk about or that I want to use in a laboratory. So there's going to be some common themes here. If you're taking the course, what you'll find out is that the terminology of these pieces and parts are the same as what you've talked about so far up to this point. If you're part of the competition, then all of these terms are going to be new to you. And what I want you to remember is that no matter what spectrometer you're talking about, for the most part, these pieces and parts are going to be present. So in a way, you're learning now what you will be learning in the future. So in the upcoming video, we'll talk about these pieces and parts, and the light source will be first.